In this lesson, we will investigate Aerodrome Operating Minima, AOM. That is, the approach and departure minima that the operator must not infringe as he seeks to conduct his air transport operation in all weathers. The operator is responsible for setting these minima, including the method he used to calculate them, and for promulgating them in the Ops Manual. However, there are absolute minima. These absolute minima are the highest of those specified in EU Ops and by the National Aviation Authority responsible for the aerodrome. With the advent of the head-up displays, HUDs, and enhanced visual systems, EVS, we examined in the last lesson, the state may publish lower visibility minima for these systems or allow operators to negotiate lower minima based upon their demonstrated abilities with these systems. Unless the authority allows otherwise, all approaches must be flown as stabilized approaches, SAP, and, additionally, non-precision approaches must be flown using the Continuous Descent Final Approach, CDFA, technique. When establishing the AOM, the operator must include the following factors in his determinations: the aeroplane, the flight crew, the runway, the aids, the equipment fit of the aeroplane, the terrain and the national authority established clearance minima, the meteorological situation, and finally, the method of final approach. Now we'll examine one of the determinants outlined earlier in more detail, namely aeroplane characteristics. Each aeroplane is categorized A to E, inclusive, dependent upon its target threshold speed, that is, the indicated airspeed, IAS, at which the pilot aims to cross the threshold. This target IAS is called VAT and is at least 30% higher than the corresponding stalling speed in the landing configuration and at least 23% higher than the corresponding stalling speed flapless. The at least refers to the fact that the target threshold speed is based on the higher of the two stall speeds, which, in turn, are calculated at the aeroplane's maximum landing mass. Often VREF is used interchangeably with VAT, although it is calculated for the estimated landing mass of the aeroplane rather than the maximum. Here are the categories with their corresponding target threshold speed ranges. In this section, we will discuss Appendix 1 to Ops 1.430, which is a detailed examination of aerodrome operating minima. There are two versions, Appendix 1 Old and Appendix 1 New. We will consider the new because the old will be obsolete in a few years. The appendix discusses each aeroplane type and category in some detail. We will approach the appendix from the point of view of the medium-range jet transport, the MRJT, used extensively in examinations. Our MRJT will be Category C, that is, a target threshold speed, VAT, of 121 to 140 knots inclusive. We will also assume the aeroplane can meet its normal performance Class A requirements. That is, if the critical engine fails during any point during the takeoff roll, the takeoff run can either be abandoned within the distance remaining or continued to 1,500 feet above the airport while clearing obstacles by the required margin. First, before the commander can commence takeoff, he must meet the aerodrome visibility or runway visual range minimum specified by his operator. This minimum, in turn, must not be below that specified in the on-screen table. If the runway meets all of the lighting requirements and has several RVR measuring sites, the MRJT theoretically can commence takeoff if the RVR or visibility is reported as 150 meters or more. Additionally, there must be sufficient visual references present for directional guidance in both reactions to an engine failure, that is, abandonment and continuation. I say theoretically because we must now consider the decision-making following a continued takeoff. Obviously, the aircraft should land and resolve the engine problem as soon as possible. Preferably, the flight crew would like to land back at the departure aerodrome. Therefore, the departure minima would have to include the approach minima and may have to increase to do so. For example, if a Category 1 ILS is the best approach option, it requires an RVR of at least 550 metres. The takeoff minima must, therefore, also be 550 metres. If the actual visibility would now not allow the takeoff, there may be another option. In order to reduce the minimum back to 150 metres, the aeroplane must land somewhere else, that is, at a takeoff alternate. We discussed alternates in the lesson on Annex 6 and the adequacy of aerodromes in the lesson on operational control. Suffice it to say that for the MRJT operation, a takeoff alternate must be within the distance commensurate with 1 hour's flight time at the one engine in operative cruise speed in still air, and at the aircraft's actual mass. If an adequate takeoff alternate can be nominated, the RVR, or visibility minimum, reverts back to the initial tabulated value, that is, in the case of the MRJT, 150 metres. So, the final question is as on the screen. The 150 metre minimum can be reduced to 125 metres if the runway is equipped with high-intensity centreline and edge lighting, and to 75 metres if an approved head-up display system is fitted. To conclude this section, here is the complete decision tree. So far, we have discussed only the takeoff, but inherent in this decision must be that we have a place to land. In this section, we will investigate 3 types of straight-in approaches: the Category 1 approach, the non-precision approach, NPA, and the approach procedure with vertical guidance, APV. First, the Category 1 approach. Here, the approach may be using the instrument, ILS, microwave, MLS, or global, GLS, that is, satellite landing systems, or the PAR, the Precision Approach Radar. The decision height, DH, minimum is 200 feet, and minimum RVR is 550 metres. Second, the APV, the approach procedure with vertical guidance. Here, glide slope information is produced by the internal navigation system, but is not generated from outside the aircraft, as is the case with the Cat 1 systems. It does have, however, vertical guidance, and so is more akin to the precision Cat 1 approach than a non-precision one. It therefore carries minima slightly higher than those of a Cat 1 approach, that is, decision height 250 feet and RVR 600 metres. Finally, a non-precision approach, NPA, has lateral guidance but neither a glide slope generated externally nor an internal one. The lowest decision height or minimum descent height is 250 feet, and the minimum RVR or converted meteorological visibility, CMV, is 750 metres. However, the decision height or minimum descent height is dependent on the landing aid used. Here is the table of system minima with the applicable minima. In order to continue the Cat 1 APV or non-precision approach beyond the applicable decision height or minimum descent height to a landing, the pilot must be able to see enough of the approach to landing area to complete the landing visually. This visual scene is called the visual reference and has as its minimum either the physical surface, runway markings, or runway lights. The physical surface that forms the visual reference is either the runway threshold or the touchdown area. Runway markings that comprise the visual reference are those at the threshold or in the touchdown zone. When the visual reference comprises lights, it means the approach lights, threshold identification lights, threshold lights, runway edge lights, centerline lights, touchdown zone lights, and, finally, any visual glide slope indicators, VASIs, PAPIs, etc. In conclusion, here is the full list. There are numerous other precision approaches with more restrictive requirements than the standard Category 1 approach we have already encountered. However, we will examine only 3 of them: the Cat 2, the Cat 3A and the Cat 3B. Category 1 approaches use ILS, MLS, GLS and PAR systems. However, currently only ILS or MLS is used for Cat 2 or 3. The decision height for a Cat 2 approach is less than 200 feet, but no lower than 100 feet above the elevation of the runway threshold, and with a corresponding RVR of at least 300 meters. Category 3 approaches can be split into 3 subcategories, however. EU OPS recognises only 2, Cat 3A and Cat 3B. Here are their respective minima. Whereas Cat 2 and 3 approaches in aeroplanes, used for commercial air transport, that is, subject to EU OPS, must be flown with a crew of at least 2 pilots, Category 1 may be flown single pilot. In which case, the basic RVR minimum increases to 800 meters. This minimum may be reduced, however, if a number of criteria are met, such as the use of an autopilot coupled with the ILS, MLS or GLS, etc. We have completed our examination of straight-in approaches and their corresponding minima. Now we will turn to circling approaches and their minima. As a reminder, a circling approach is one where either the approach procedure is not aligned with a runway or is not aligned with the desired runway. In both cases, the pilot manoeuvres visually at some point during the instrument procedure to land on a non-aligned runway. The minima for landing is expressed as a minimum descent height, MDH. That is, a height above the aerodrome which serves as the limit for descent unless the pilot has the applicable visibility for circling then for completion of a visual approach. To convert the MDH into a minimum descent altitude, MDA, the aerodrome elevation is added in. The aerodrome rather than a runway elevation is used because the circling minima are applicable to circling approaches for any of the runways. Minima rather than a minimum are mentioned because each minimum is applicable to a particular aeroplane category, A to E inclusive, as we have encountered earlier in the lesson. We can see the relevant figures highlighted on screen. EU OPS requires the MDH and the applicable visibility to be calculated as the higher of 3 sets of figures. The first set considered is the obstacle clearance height, OCH, published on the chart with its applicable visibility, which we have highlighted for our Category C MRJT. The second set is the minima for the instrument approach used to descend to the aerodrome. Only in very few cases, and the author cannot think of one, would the straight-in minima be higher than the corresponding circling minima. The final set is that given in a table in EU OPS, shown here. Circling in Cat E aeroplanes is by implication prohibited. If the calculated minima for the MRJT are those shown in the previous table, that is, MDH 600 feet and visibility 2,400 meters, when the aeroplane is level at 600 feet above the aerodrome, the pilot must have an in-flight visibility of at least 2,400 meters to visually maneuver for a visual approach to the desired runway. The minimum visibility to undertake a visual approach is RVR 800 meters. Of course, if already operating in at least 1,500 meters, the minimum for a Category A aeroplane, this minimum should not present a problem unless operating in conditions of shallow fog or low drifting sand or snow. This concludes our investigation of aerodrome operating minima.